I work in Bayer Pharmaceuticals. I'm a head of data science, and now I'm going to start a presentation together with Ghaith. So let me share my screen. Just 1 second. I will share. Okay. To go in. Okay. So our presentation is about the concept of explainability and interpretation or interpretability of models, which is a topic that is becoming more and more important in the last period. Let's start first of all trying to understand the reason. If we think about models and systems, there are some fundamental questions. We have a reality. We have a nature all around, and we are used to model the reality by creating this connection that we call grounding. So we take some input to the model, taking the input from the environment. The model must represent something, must produce an output, and the output must be matched with what happens in reality. If this is confirmed, the model works. Otherwise, the model must be modified. So a model in general is a mathematical set of equations, for example. And the first question that normally we ask is what's inside the box? We want to know how X is associated to Y. So which rules are there? And this is very easy in some cases. For example, if we think about models like, I don't know, a physical model where the acceleration of a body, we know that it's a simple equation. We know immediately how Y changes when X changes. But in general, the question is, what happens if X change if I don't know what's inside this box? So in this case, we have to start with a concept to put together human beings and AI, because AI itself doesn't need any explanation. AI works and it doesn't need to be explainable. AI must be explainable because there are human beings that are exactly on the other side where the Y arrives, and they ask, how is the model associating Y to X? So to try to understand this, we have to clarify some fundamental concepts. First of all, the concept of interpretability. Interpretability of a model means that a human being, clearly an expert, but a human being, is able to understand in human terms the outcomes and how these outcomes are obtained. The way can be even complex, mathematically related, that doesn't matter, but a human being using a specific domain knowledge can do this. This is the example that I made before, for example, if, the physical laws. In general, when instead we move to models where this function is extremely complex, it's not very simple function, like a deep neural network, we move to the concept of explainability, where the human being needs another tool that we can call explainer that can produce comprehensible pieces of information. So these explanations are not originally obtained by interpreting directly the model, but through another component. And the third element that we must take into account is the transparency. In other words, the concept of transparency can be summarized as the answer to the question how difficult it is to reproduce the internal dynamics. In other words, if I have a model and I can immediately create another copy of the model using a different system, the model is transparent. I can look inside. It's like, imagine your car. You can open, you can see the engine, you can take every component, put everything together and reproduce your car. But when we are in front of a black box, the transparency starts becoming from white or transparent to gray and to black, at that point, it's almost impossible to reproduce the internal dynamics very easily. I mean, so that's why we work by plugging in the explanation module. The explanation module is a component that is put aside to the model and will analyze. There are different techniques, and Ghaith will explore some of them, but we'll analyze how X is associated to Y by producing an explanation that I denoted using this letter epsilon. The explanation itself is an abstract concept, because the explanation can be something concrete. For example, a heat map that shows if you have a deep neural network, you will see some examples, can show some regions that affects the output. Or the explanation can be something like related to the importance of the features. So the explanation is in general something that will help the human being understand how the model is working. So now let's start at least to try to answer this question: why do we need explainability? I thought about this concept, and I arrived to this conclusion: human beings can have an understanding ability that can increase, and starting from the natural language, which is the easiest way we interact. If I tell you there is a tree in the garden, even if you are not familiar with the garden, you can imagine what I'm saying. But if I tell you there is a tree, I don't know, in the sea, or I mean a tree, not a dead tree, a real tree in the sea, you with the logic you say, well, this is something that doesn't hold, so there's something wrong. Then I can start increasing my complexity, for example, with arithmetics or simple level of mathematics, or can I arrive to calculus and even more complex techniques. So what we are doing is starting from examples, which are the easiest way to explain something. This is like this. So if you have an idea of the object A, and I tell you that the object B is approximately similar to the object A, you can easily understand what the object A is, the object B is, sorry. But at a certain point, we need abstractions, and we need initially low-level abstractions, so abstractions that are easily manageable. But what we need at this point, when we try to work with systems whose complexity is growing, high-level abstractions. And this is the case where we are in this moment with explainable AI. We can also find some very practical reasons. Each stakeholder, when I say stakeholder, I mean imagine the explainable AI in its applications. So it's not for the practitioner, but for the user. So each stakeholder speaks their own language. If you talk to a physician, the physician doesn't want to know what a convolution is. The physician wants to know why a lung is, or a region of a lung is the cause of a cancer. Domain experts, so for example, again, the physician can either confirm or reject the outcomes. We still need domain experts to understand if the model is arriving to a conclusion, so to an outcome, because of features which are really inside the model or inside the data, or for example, it's arriving because of other reasons which are completely different. For example, labels put on some images that can make the difference, but clearly they are not important. So another extremely interesting thing is that users can trust a system. Trust is a concept that is very strongly related to AI ethics also. So when we explain, we also expose the system to the possibility to show biases and errors. So we are not hiding anything. We are providing the way to discover biases and errors, and so we can increase the trust in the system. And another thing that we need to consider is also a direct consequence of the high-level abstractions. Human perception cannot manage multidimensionality, and this is not necessarily related to images, for example, or volumes, so hypervolumes. But in general, when you have to manage too many things altogether, your brain starts having problems. So you need to split into different components, and you need this kind of techniques to have a control over the topic. So the simplest explainability, well, I want to show this example. It's the linearity. If we have a function which is just a constant plus the summation of some terms which are proportional, we have a constant term of proportionality a of high times the covariates xi. The variation are just equal to AI. So we can immediately, using the first partial derivative, understand that the contribution, if all the values xi are in the same range, the contribution of each xi is weighted by AI. So in this case, it's obvious that if I tell you the model is 1000 x1 plus 10 x2, and x1 and x2 have the same range, you clearly understand that x1 is much more important than x2, because the constant is a weight in this case. But for example, let's suppose this thing here, imagine to work with this thing here. It's just an example. Here we have an hyperbolic tangent of a summation plus another term where there is a square. In this case, if you do some calculation, you obtain that the contribution, the derivative of y with respect to each single variable is, first of all, is much more complex, but the worst thing is that it depends on all the other terms also, because we have to consider the derivative of the hyperbolic tangent of its argument. So in this case, this is the real problem of deep neural networks. A deep neural network, for example, with 100 million parameters or even more, becomes something that cannot be understood in any way without specific models and techniques. Sorry. Another thing that we want to consider is the causality. And this is a very, very interesting thing, because imagine that you have a model. In this case, we have a generative model. So we have a model where we have the probability distribution of x given a set of labels y, parameterized using this set of variables theta. And this model can be easily swapped using the Bayes theorem. And we have three components where the probability of x is the marginal probability of the sample subspace. It's in other words, is the density estimation of the sample subspace. It's helpful to understand how our sample space is structured. But then we have also the generative model that we can easily write as a probability of x when we assign a certain label. But we have also the discriminative model, which is also the classifier, the classical model where we want to know the probability of the y given a certain x. And this is something that we want to analyze a little bit in more detail, because in general, standard models rely mainly only on correlations. In machine learning, correlation is very common, not causation, because correlation doesn't imply causation, but vice versa, causation imply correlation. So the explainable AI is also focused in trying to understand if the relation probability of y given x is a causal relation. because using some specific techniques, we can arrive to discover this. And if we discover this, we know that if X has a certain value, this causes Y to have a certain value. And even if this can seem very similar to a correlation, we can perform another step, which is extremely helpful in practice. And the step is about using the counterfactuals. So in other words, we want to understand, if you look at this expression, we want to understand the probability of a certain outcome when we modify the input. And when the modification in general is, for example, if we have some parameters, we keep some features with the same value, or we change some other features. And I just want to make you an example. A physician can, for example, think, what happens if I change the therapy? What happens to the progression of a disease if I add another drug? So answering these kind of questions becomes easy if we can use counterfactuals, but only if we can confirm the causality. Otherwise, everything is not well-founded, because in that case, if there is only a correlation, this is not necessarily true. So the causal question is clearly, what is the cause of a particular outcome Y? And this is very helpful. In general, is the classical question that we ask immediately. But in the second stage of the process, when the domain experts come into the scene, is also asking the counterfactual question. Sorry, when I moved. And it's, for example, what happens if the outcome Y? What happens to the outcome Y if I change the input? So this is another extremely interesting topic, and the research is focusing a lot of efforts in trying to improve this kind of elements to increase the possibility of human beings to understand how the system works. Another, and this is another important, extremely common way to apply explainable AI, is explaining the features. So if we have, for example, decision tree, you know that decision trees are extremely common, and they because they are very easy. I just put this example here, which even a person without any knowledge can understand. And there is also a way to classify the features using an impurity criterion. In other words, if a feature using a certain feature, we can arrive to a split where we have a higher level of purity. So samples belonging only to a class, that feature is more important than another. But this is only for decision trees, or for other models where it's possible to use an averaging or something like this. But in general, we want to have the same approach also for any generic nonlinear model. And this is one of the applications that Ghaith will show that is extremely important when we want to understand how some features can influence the output, even if you are using, for example, a deep neural network. Last thing, and I leave the stage to Ghaith, is the concept of the contraposition of local and global explanations. In general, when we have a certain hyperspace where the sample space is very, very large, in general, we don't need to work with all the possibilities of explanations. So global explanations are in general extremely have an extreme high computational cost. But in what we do in general is to work with local explanations, so with methods that can find an explanations. Of course, they analyze the model, they find some association rules, some techniques, some information that can be helpful, and then allows to use only a single small region, where, for example, in this case, we want to analyze only airplanes. So we put the input is an airplane, and the model will show that classify the image as an airplane because of the wings, for example, or the tail. So in this case, it's possible to work with very high dimensionalities without an extremely high computational power. So thank you very much. I stop here, and I ask Ghaith to take control and to continue the second part of the slide of the presentation.
Okay, thank you, Giuseppe. In fact, the camera was showing that my camera is on. I'm sorry if it was on. It's totally by mistake. I will share my screen also to continue, and thank you for all of this. In fact, I enjoy it. Even we work together on it, but I enjoy listening to you. I will continue on this to explain, let's say, some kind of my vision about explainable AI, and also just to tell some other facts. I will start from here just to know, in general way, what is the target of using explainable AI. In fact, from my personal point of view, I prefer to tell that the AI is able to be explained, but I'm not like this term explainable AI, because we have a feeling that there is something else. It's not the same topic, or it's not something else. So we are talking about how to explain the AI. Now, the main target that we have is to show evidence to the business stakeholders, final users, about model performance. Sometimes this is very important, especially if we are talking about the medical sector. It's very critical sector. So in this kind of business, we need to show them something, to tell them that, okay, this is the reason of this decision or of this prediction. The other point is to understand the model in a better way. And most of the samples or most of the techniques that explained by Giuseppe, it was about this, because we as deep learning engineers or machine learning engineers, we need to understand why this model is acting like this, and where is the wrong decision, or where is the, let's say, the fatal point about this model. So according to that, yes, sometimes we find that the classifier might make good classification, but at the end for a wrong reason. Also, according to that, this will not be accurate. But the accuracy here, it will not be correct. Now, is it something that we forced to follow? Okay, let's see. I have some examples, some techniques that will be used, and then I will just make some comments about each and every technique. First of all, all of us, we know what is the structure of the neural networks, which is used for most of the machine learning, not machine learning only, for deep learning also modules. So according to that, we have input, we have layers, we have nodes for each layer, and then the output. So the explainability, it will be playing on one of these parts. That means we are talking about either we are going to explain the model performance by understanding or studying, analyzing the input, or by analyzing the structure with the input, structure of the neural network with the input, or by just changing something about the output and to understand the correlation or the causality of the input, why the output is reached like this. So according to that, we are able to categorize that explainability or interpretation methods into methods mainly, or 4 categories. The first one is perturbation based. That means we are changing on the input, and according to that, we are changing something in the input, doing some changes to just know or understand what will happen to the model, and from that we can understand the model in a better way. The second method, it's function based, meaning since we are looking for the neural networks as a function, so we are unable to do anything until, just a moment, please. Yes, later, please. Sorry, I have just interruption from my family. So, okay, if we are looking for machine learning as a function, according to that, we are able to approximate this function to get explainability for this. There's some samples also, which is Taylor expansion or gradient time input as other examples. The third explanation category, we are the structure based, and this one is really, really very interesting from my point of view, and I like it very much. I find it's really nice way to explain the models. And the fourth one is the sample base, which is the most famous framework for that. It's the line. Now, if we are talking about the, let's say, the input perturbation methods, we have the old, very famous sample that you are able to make some masks and to the image, and then run the model, and according to that you can study what will happen. That means we are looking for a castle. If we mask this part of the image is still a castle, this part is still a castle, but if we mask the castle, then we understand that this part of image, this feature is the most important. Now, first, this is very, there's some problems on this method, and it's not that much used right now. But first, it's very slow because you have to run multiple masks. This is the first. The second problem is it may introduce artifacts, because sometimes the decision or the classification, it will happen for two parts of the inputs, for two features, not only, or for two parts of the image, not only this part that we are masking. And also it's assume locality. Sorry, assume locality, that means we are looking for two parts and then the mask will come with one part. Introduce artifacts. In fact, let's say we use a square which is gray square, and gray square over the hill, it might be castle also. So this might make another problem. So it's unable to rely on it. But on the other hand, there is a replacement for it. This is right now my comment on it. There is a replacement that each time we are doing data augmentation, especially for kind of image classification, we are doing data augmentation. So according to that, yes, the feature engineering and the data augmentation can do the same without thinking about it as let's say, explaining method. But the most interesting one in this part, it's the SHAP, or the Shapley values. The Shapley values is something that it's plugged in on the model, using the model outcome and the data to just give explanation about the prediction. Now I will just move this to show what's the output of the SHAP. I'm not going to explain a lot about how it's be calculated, but at the end, the good thing about SHAP, it's having all the expected changes that might appear in the input. So all the prediction, all the probabilities, it will be there. And according to that, it will give us clear idea about the feature importance. And this is really very nice about SHAP. Now, there's other problems. Sometimes it's considered slow, but when you have this kind of, let's say, plots telling you that you have this features, and this is the importance of each feature, and also which kind of importance, if it's positive decision or negative to the decision. In this way, yes, you have clear understanding, or it's interpreting the changing of the inputs and how it's affect the output of the model in a very nice way. And the good about SHAP, it's also suitable to be used with most of the famous framework on Python or on R, and also it's come with multiple methods to show the plots about it. And really, it's showing great, let's say, evidence about the feature importance. But all of this, we have, if we want to have clear idea about it, we have to study the explainer, we have to study SHAP and understand how it works. Then we are able to, let's say, use it or plug in on the model that we are working on. The other method, it's the function-based. Just like we are talking about the Taylor expansion. In Taylor expansion, we are trying to approximate let's say, the function that we are, if we are consider the neural network, the full neural network or the full model as a function, we are trying to approximate it in a way just to find some clue about this. The problem here, when you are approximating, we need a root point for this approximation, and this is not easy to find if you have multi-dimensional data. And the Taylor expansion, in fact, if we want to go, I'm not going to go too deep on that right now, but we have the resources, we are able to share it later. We know the problem about it, it's needs a root point, let's say a valid root point to be worked, but it will be used later in the structure-based, because the same concept, it will have better performance for another way or another category of explanation. And also the problem about this, it's the gradient shattered, because if we have very deep neural networks, the gradient, it will not be suitable to be approximate. The other method, it's gradient time input. Here, it's just it's very fast method to explain the model. We run let's say the classifier, for example, and we get the output, and according to that, we are going to find the gradient and multiply it with the input, and according to that, we can reach for a kind of explanation. The problem about this is also with the deep neural network, the explanation will be very noisy, so it will not be helpful or showing clear explanation about the model. But so this is the function based according to the current situation. This is the, let's say, disadvantages of the function based. But we have to enhance it, or we have to study how it's enhanced to the structure-based explanation. And in fact, we think that it's enhanced to structure-based explanation, but structure-based explanation is one of the first explaining methods that appears. So it's something engineers or data scientists start work on it from the early days of need the explanation for the neural networks model, or for the black books of neural networks. The idea about structure-based, and especially we are talking about layer relevance propagation, layer-wise relevance propagation. The idea is, if we are unable to get the function base for the full model, then we understand that this neural network at the end, it's layer-based, and for each layer we have neurons. So we are able to study or to distribute this function over the function, over smaller function for each layer and for each node in the neural networks, and then get the output of this function in propagation way. That means from end to the as back propagation, from the output to the input, and then in the input we will get a clear explanation that understanding the structure and also the input in a better way. So in fact, if we have this kind of classifier, for example, we have image classifier that tell us that if the image is cat or roster or dog, and then we sure that we got the output, it's roster. So we are going to distribute this to the suitable neurons that affect this decision, which is activated for this decision. So how to make that? We have two main factors that it's clear that it has this, it has built this decision. The first one is the activation for each neuron, for sure it's built this, and also the weights, which comes from the training. So in fact, for example, this activated neuron, it might be participate on the decision, but the next one, it's not participating because the weight, it was very low, so it's participating on the cat decision. So from doing this, and also for some cases, you are able to modify this function to have just consideration for the negative and positive values. That means if sometimes it's the model, it's telling you that this is not a roster, that, for example. So for this modification, you are able to back again and distribute the final classification value and distribute it for the neurons until you reach to the first layer, to the output. And by plotting this or by showing this value, you will get, for example, a heat map. This heat map showing which part of the image make the decision for this. So in fact, in the rooster, if we run for this, we'll find that maybe the head of the rooster is the reason for this decision. And in this way, the structure of the neural networks, it's play main role here. The activation and the training results, it's the training weights, it's play the main role. And also it's fast way, it's not slow way, because it's one run and it can go. The other good point about this, that it's able to be run another clustering method after it, because we are talking about run for each sample in the data set. But if we want to run all the samples, so we are able to go and make a cluster, and then this cluster will tell us explanation about it will cluster the explanation itself. So we can find that this is 3 or 4 clusters tell us that, okay, here the rooster head, it was the reason, but in another way, in other images, maybe the flowers, it was the reason for this classification. Now, there is some mathematical proof about it, and we can check for each and every layer what is the formula it will be, and also it depends originally on the Taylor expansion. I'm not going to go in depth on this for the time, but if anybody wants to provide some papers or something, I'm able to provide it to you. Now, what is the advantages and disadvantages? The advantages, it's fast way. It's able to be used for supervised learning and also for some other machine learning method with some tricks done. In fact, I have to mention this in the reference and I forgot. They make kind of neuralize, for example, for the KNN. So that means any machine learning method, it can be seen just like in neural networks, and according to that, this method, this explanation method, it will be used. And for example, this image is, it was correctly classified as a horse image, but not because of the horse shape, because of the copyright of the image, because the data set has a lot of copyrights, and this was the main reason. And here's showing us that how this decision done and why it's, even if the total accuracy of the model is correct, but with this kind of explanation, it will not be correct. Now, what is the disadvantages? This heat map method, this plotting method, for example, if we use another method, we will find another result. If we use another method of heat mapping, and this is why sometimes we as machine learning engineers, we are cheating. We are using another method to generate the heat map. And in that way, maybe we'll find another explanation. And here's the conflict to appear. Now, for this one, we have mathematical proof. It's valid method, but at the end, if we are talking about non-expert person, we are talking about physician, for example, what will exactly tell him if we are using a robust or trusted method for explanation, or we are just showing him the suitable explanation? Now, this is all of this question, as I told you in the beginning, because I don't want to go and tell that we need explainable AI. What we need to explain the AI model, not to work on explainable AI. This is my idea, let's say. Now, this is, okay, just to continue. Now, the third method, it's the sample base. And let's discuss about, or speak briefly about the LIME. In fact, the LIME, it stands for local, interpretable, model agnostic explanation. Local, that means it's working on some local input. That means it's not the full, it's not global explanation. That means it's not explaining the hyperparameters and why. So no, it's local. It's speaking about the samples that we have. Interpretable, because it can show interpretable in an interpretable way. Model agnostic, because it can work on any model explanation. Now, the LIME, in fact, the algorithm of LIME, it's working like on the following step. First, permute the data. That means we are generating new data, and then calculate the distance between permutation data and the original observation. Then make prediction for the new data set that we generate. Pick M features, or the most important features, describing the complex model outcome from the permuted data, and then fit this sample model of the M feature and check the similarity score as weights, and then the features, it will give you a better way for the explanation according to that. Now, again, it goes under sample-based. That means we have original data set and we are generating another method and to find the explanation. Now, the great about LIME, first, it's considered faster than SHAB. SHAB, maybe it's more general. It's I'm not going to tell that it's more global, but it's more general. LIME, it's really local, and also it's running over all, let's say, the models expected. that you are able to run it even for forestry, random forest trees or something. But at the end, what is the problem about the line from my point of view? Again, it's because it's not considering that structure. I think if we consider, I don't have a proof about this, if we consider the structure, if we go with the structure way, we are able to understand even how the structure play main role in the decision. And this is might lead for modification on the structure that you are going to use. Now, this is, we are talking about the current scenarios, right? If we move just before the critical thinking in the future or in the near future, we are able we need to explain some models that we are using, the models generated from big companies like, let's say, Microsoft or Google or something. So we need the explanation because it will give us a clue. But what is my critical thinking about it? That almost or always the engineers, they are trying to explain their work before they are doing it in the design time. For example, LSTM, it's appeared before the GRU. Even the GRU is simpler because all of us, when we are building a model, we try to say that start with the simplest model and then go to the, if it's not work in correct way, you are able to understand your experience and go on the better way. But at the end, if we study the history of these models, we find that always we start with some kind of complexity and then we simplifying it because the engineer is trying to explain their work in their mind or for themselves before going and generate the models. So according to that, really explainable AI is important for the specialized people. I'm not thinking that, I don't think that it will be important for stakeholders or final users like physicians, because I'm focusing on healthcare that much, because at the end, just I will give one example, which comes from my friend Tom Ives. When I go to the home and just switch off the electricity, I don't have to explain, I don't need somebody to explain to me why the light is on. So there is the reference of this from our side. Thank you for us, and I hope it was good for everybody. Thank you.
Thank you, Ghaith and Giuseppe. I think everybody has definitely enjoyed this talk, and you have so very well explained how explainability, interpretation, and causality in AI can be brought forward, and how these different technical details of every model that you have tried and put in this little session, with LRP, SHAP, or any other methods that you have been using has been really great. I think people have got such insights which will give them a deep insight and thinking which model they should be using, definitely, and how a model can be explained in a structured manner. That is the key thing, how you can get the positive and negative outcomes of them, and how to have trust in your AI model, and feature engineering and the pre-processing that you have been using, especially the rooster example. I'm really blown away by that one. Thank you for that one. And I would invite Richard to call upon the next speakers. And thank you for your speech. It is really interesting. And I hope people would look forward to more details.